Okay. Here we go. A Merry Christmas, everybody. Here, let me get the stream up for you. I have friends watching me this time.
Boy provides a modern introduction to quantum field theory. This comprehensive video develops a standard model of particle physics and explains state-of-the-art techniques for performing precision theoretical calculations.
That's true. No, I'll just take the drones. Why
All
didn't
right,
I eat
part 1,
this?
field theory, chapter 1. Actually, we're skipping chapter 1. You don't need to know about chapter 1.
Educational.
All right,
You
chapter
can learn
2,
about R.E.P.O and this.
Lorentz invariance and second quantization. In the previous chapter, which we skipped, we saw that by treating each mode of electromagnetic radiation in a cavity as a simple harmonic oscillator, we can derive Einstein's relations between the coefficients of induced and spontaneous emission without resorting to statistical mechanics. This was our first calculation in quantum electrodynamics, QED. It is not a coincidence that the harmonic oscillator played an important role. After all, electromagnetic waves oscillate harmonically. In this chapter, we will
So much
review
stuff
special
up here.
relativity and the simple harmonic oscillator and show how they are connected. This leads naturally to the notion of second quantization, which is a poorly chosen phrase used to describe the canonical quantization of relativistic fields. Lorentz invariance. Quantum field theory is the result. Oh, we're going to set h bar equals c equals 1, by the way. Natural units, lol.
Yeah, obviously.
Yeah. Quantum field theory is the result of combining quantum mechanics and special relativity. Special relativity is relevant when velocities are a reasonable fraction of the speed of light, v(ish) equals 1. In this limit, a new symmetry emerges, Lorentz invariance. A system is Lorentz invariant if it is symmetric under the Lorentz group, which is the generalization of the rotation group to include both rotations and boosts. Normally, the more symmetric a system, the easier it is to solve problems. For example, solving the Schrodinger equation with a spherically symmetric potential as in the hydrogen atom is much easier than solving it with cylindrically symmetric potential, such as for the hydrogen molecule. So why is quantum field theory so much harder than quantum mechanics? The answer, as Sidney Coleman put it, is because E equals mc squared. This famous relation holds for particles at rest. When particles move relativistically, their kinetic energy is comparable to 2 or it exceeds their rest mass, E kinetic is greater than m, which is only a factor of 2 away from the threshold for producing 2 particles. Thus, there is no regime in which the relativistic corrections of order v over c are relevant, but the effect from producing new particles is not.
Okay.
Lorentz invariance is symmetry under rotations and boosts. If you get confused, focus on perfecting your understanding of rotations alone. Then consider boosts as a generalization. Rotations should be extremely familiar to you, and they are certainly more intuitive than boosts. Under two-dimensional 2D rotations, a vector xy transforms as x arrow x cosine theta plus y sine theta, and y is minus x sine theta plus y cosine theta. We can write this as P matrix with two columns and two rows and one column. Arrow is x cosine theta plus y sine theta. Next row, x sine minus x sine theta plus y cosine theta equals a 2x2 matrix consisting of orders left to right, first row, then second row. Cosine theta, sine theta, minus sine theta, cosine theta, another matrix, which is a 2x1, which is xy. When an index appears twice, as in we'll be using the Einstein notation, i.e. meaning if you have the indices top or bottom, this book is stupid. It uses bottom, but that's not technically correct because you can't sum over two either vectors or two covariant vectors. So that's not how that works. But because we're not dealing with curvature, doesn't matter. And by curvature, I mean we're using Minkowski metric, which means your metric is just minus plus 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 or whatever thing you want to use. So that's just a note. This book is funky. Anyway, contraction is so if you see like let's just say xj and yj, then you would sum over the indices, i.e. if x was like a 3 vector, it'll be x1 y1 plus x2 y2 plus x3 y3. But because we're dealing with special relativity, we're dealing with 4 vectors, and the basic understanding of 4 vectors is that there's a spatial component and a temporal component. So like the momentum, it's like the temporal component is either energy or mass, depending on whether you're in the rest frame or not. And then for that's for equals mc squared, by the way, comes from that. There's also mostly it's the Lorentz invariant quantity is usually sits in the temporal location. So yeah, it's like how like literally like the positions are no longer x, y, and z. It's t, x, y, and z. More like minus t and x, y, and z, and also a c term is thrown in there. That's because time has to be negative for your geometry, your space-time geometry makes sense. So that's all you need to know. Next. Blah blah blah. All right, 2.12. Lorentz transformations work exactly like rotations, except with some minus signs here and there. Instead of preserving r squared equals x squared plus y squared, no, yeah, plus d squared, they preserve s defined x squared defined as t squared minus xy squared minus y squared minus z squared. Like I said earlier, you can have something called a metric convention, where as long
Two
as like time
coins.
and space are opposite signs, it's completely fine. So remember, there's four things. There's time, and then the three spatial dimensions. So then you can have minus, plus, 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 and then plus, minus, minus, minus. This book uses plus, minus, minus, minus for some reason. I prefer keeping the space plus because it's more convenient to think of it as that way. But yeah, the whole point of it is they want to keep your space-time interval, which is your because of now time is very much correlated with space. You have to realize that time is just another aspect of the geometry of space itself. And space is not space, but you really have to think of time as just being another aspect of space itself. Like space and time are very coalesced as the same thing.
Yeah.
So it's like there's a whole positive special relativity is that there's no such thing as a global like time frame anymore. Is that there are time coordinates everywhere, or time coordinates each. The specific definition is that your coordinates are only defined at a point, and a very specific like mathematical point things are defined. So at that it's fine, but if you try to define it globally, it gets fucked. What that means for you, and that's more gets into general relativity. More you need to understand for this is that if Sally's going near the speed of light and you're not going to speed of light, Sally, you're experiencing time faster than Sally because Sally's proper time is slower than yours.
Yeah.
I.e., meaning the way you experience your proper time is relativistic to how you're experiencing it, and you can experience time different based on your velocity. That has to deal with the fact that there's a limit to the speed of light, which means you have to normalize your coordinate transformations to that, meaning space and time kind of fuck with each other. And that's what a Lorentz transformation is. It's this because there's a thing called a Galilean transformation, which is just the way we did it before, where it's like if you throw a ball, you can define a inertial frame for the ball where the ball's not moving, but the world is moving around it. But that doesn't work because the speed of light is constant no matter what. So a source producing a thing that will go the speed of light won't go faster than the source like producing it. Like if you threw that ball off a train, then the ball will have the velocity through it and also the train velocity. That doesn't work for light. Like light is just the limit upon which it'll be just done at. That's the second positive special relativity, meaning that you have to normalize things, your coordinate transformation, so you don't have things faster than the speed of light.
Yeah.
And yeah, also light doesn't experience time because its technical proper time is like infinity. It's just not definable, so it doesn't really experience proper time. Like it experiences nothing. I don't know. The math just says zero. Like because I have to go over special relativity. I mean that's important. We are doing QFT here, but so a thing you learn about special relativity is a thing called light cones. There's three different things an object can take. Well, actually only two of them. Time-like, which is just everything that isn't light, is within your light cone. There's null light, which is light that exists on the light cone, which i.e. just taking the furthest, the most extremes of all options possible. Because if there's a speed of light, that means that you have a certain range of things which you can take on, i.e. meaning like if I like have like a ball, then that ball has a cone of possible options because it can't go faster than the speed of light, which also puts limits on information. But if there's an object outside of like a light cone that doesn't intersect with light, like your light cone would be called space-like. And space-like things cannot causality like go with each other. So if like a supernova happens like 10 light years away, for all intents and purposes, it doesn't exist to us because it causality cannot reach to us because basically special relativity just posits information cannot travel faster than the speed of light. And also posits space and time are the same thing. And it also throws a bunch of these like temporal aspects of nature that are like the same. Remember E equals mc squared, meaning you can just generate mass out of energy. i.e. you can generate particles out of energy, which is very important. This is just special relativity though. General relativity is like, okay, we have these like locally defined thing. How do you deal with gravity? Because gravity is a globally defined theory. So then you have to define a global theory locally. we didn't get into curvature, which doesn't matter. Although knowing what tensors are will be important later. So anyway, Lorentz transform. Yeah. So anyway,
I
the
love
Lorentz group is
tensors.
a group. Remembering a group is just a set of numbers, a principal action associated with them. Dane muted lol. All you need to know about groups is that they're very physics, because they are very good ways of talking about symmetry within our systems, i.e., meaning like rotation. You know, if you're on like a sphere, like God, how mathematically am I going on this? Let's just say you're like you're on you're a bead on a sphere. If you move just constrained to the sphere, you're emitting SO3 symmetry, because you're just you could just rotate it around, like, because there's still consistent symmetry happening there. Symmetry's really funky to explain. Yeah, symmetry is just like things kept the same and independent degrees of freedom. So it's like spherical symmetry means that like the only thing that's kind of dependent is your radius. If you are even dealing with radius, it's just homogeneous source. Anyway, symmetry.
Oh my god, a third Coleman
And by
box.
the way, so the Lorentz symmetry is the Lorentz group presented earlier is ones of boosts, rotations, and some other, and yeah, boosts and rotations, which is the Poincare group, which is another fucking group. Anyway, instead of 3 vectors, we use 4 vectors. T, X, Y, and Z. We generally use Greek indices for 4 vectors and Latin indices for 3 vectors. We write x of 0 for the time component of a 4 vector. Lorentz transformations acting on 4 vectors or matrices, capital lambda, satisfying. I don't want to say that out loud, but if you take the trace of it with the metric, you'll get 1 minus 1 minus 1 minus 1. In this and future matrices, empty entries are 0. G mu nu is known as the Minkowski metric. Why use G mu nu? It's actually eta mu nu. There we go. Sometimes you write eta mu nu for this metric. With G mu nu, oh, by the way, mu nu, I mean it's in the sub indices. So it's like you write G and then mu nu and then like the sub index. Get used to the fact that if you have like a higher indice, it does not mean exponent. That is really the case. You just kind of have to learn the fact that it's either a tensor, and it does not mean fucking you're like raising it to like a mu variable power. This is a purely audio-based thing, so good luck. Yeah, anyway, G mu nu is known as the Minkowski. Well, no, eta mu nu is known as the Minkowski metric. The G mu nu is known as like the general metric, which is the defining thing you can do GR with. It's trivial in QFT for 95% of it, so you don't have to worry about it. It holds the property that if you if you sum over both G mu nu indices with itself, it equals 1, because that's literally what's defined to do. Because the G mu nu defines your metric space. No. It defines your inner product space, i.e., meaning, you remember Pythagoras theorem, where it's like a squared plus b squared equals c squared, like that shit. That's definable by the metric, because it's actually like your metric is 1, 1. But so basically, metric tells you how does your Pythagorean theorem evolves as you go across different locations. But this is not a general relativity discussion. I just like to mention it because it's cool, and also does explain things. Cool. There's boosts. I'm not reading these out because they're just a bunch of hyperbolic trig in there, and who cares? Blah blah blah. Rapidity, scalar fields. Scalar fields are functions of space-time that are Lorentz invariant, which makes sense because scalars are a single number, so it doesn't matter how you transform them because they're a single number. Remembering scalars is just a number, vectors is rank 1 tensor, or like, actually I haven't really explained vectors. They have 4 components because special relativity, and then tensor is just used for things after that. That is under an arbitrary Lorentz transformation. And by the way, understanding of fields is you have functions before where it's like you insert a number and you get something on the y. So you have like y equals 2x, you put x, you get y equals 4.
Yeah.
Fields is you assign a point to each point. So it's like a field would be like, let's just say like, let's call the M field. And it has, well, if it's a scalar field, we can define it as like 5x plus 2y. So then each point on a 2D plane will have a value associated with it. Well, like functions just spit you one value at each point. a field will have a value at each point, and then vector fields are just when you separate that. So like each component of a vector is defined by random Cartesian variables, depending on whatever coordinates you're using. Also, there's another thing with coordinates that you can use, because another thing of general relativity, or I guess special relativity, is that you can define your coordinates to be normal. Doesn't matter here. Don't worry about it. Yeah, coordinates are important because you want our variables to be coordinate independent. Because that's why tensors are useful, because they have like coordinate dependence, like independence baked into them. Because tensors are true values, i.e., meaning that you can use whatever coordinates you want, but it's not really going to do much to it. Because scalar fields are like they're going to remain the same because scalars.
Oh no.
Okay, sometimes as used. What's going on with the game? Doesn't matter. Which is used, which makes it seem like the scalar field is changing in some way. It is not. Well, our definition of x mu, which 0, 1, 2, 3, 4, remember that, changed in different frames, i.e. apply the Lorentz transformation, and by the Lorentz transformation oppose the symmetry of the Lorentz group, which all you can think about is it keeps the space-time interval constant. And the space-time interval is just Pythagorean theorem, but in reality. But like physically, because it's defined by s squared equals minus t squared plus x squared plus y squared plus c squared, because that's how you define distance in space. And because now time is a geometric aspect of reality, you also have to measure the geometry of time itself. Wibbly wobbly, squibbly wobbly, timey-wimey stuff.
Skibbity toilet
Anyway,
stuff.
Skibbity toilet relation, too. And so the Lorentz group, remember I said group is a thing with an action that keeps itself consistent within the set of things itself. The Lorentz group keeps the space-time interval consistent, which is what we want, because you know what Lorentz transform something now it's completely different, because that would be nonsensical. That's like if you did transformation, Sally's going 50 more miles than earlier. That's no. When you do these like transformations, you're holding the system, the quantities of the system the same, just doing it different. Like you can define a sort of physical system, at least most of them, to have an inertial frame. I'm meaning like if you throw a ball, you can see that, oh, that ball is moving that way, or you can define a frame for the ball where the ball is not moving, it's just the world is moving around it. Inertial frames are very important because they're not definable for light, which means there's a limit to them. Also, light has things to go at the speed of light must be massless, because you do math and you find out E equals mc squared. It's like actually E squared equals m squared c cubed plus p squared c cubed again, I think. Yeah, i.e. meaning energy depends on your mass, and that means if you have mass, you can't reach the swag speed of light limit. But there's that p squared though, which is why momentum, that's why photon in light is defined by its momentum and not its mass at all. Can things become massless? Not people. Particles can be, if under very, very strict that on the end of this. So, while definitions of x mu changes in different frames, you apply like x mu nu to a Lorentz transformation, which just looks like capital lambda, which looks like an upside down capital V, mu on the top indice and mu on the bottom indice. Then you have x mu, meaning you summed over the components that correspond to mu, and capital lambda and components in x mu. This is really fucking hard to say verbally. Write it out. The space-time point labeled by x mu is fixed. The equations are invariant under relabeled coordinates tells us absolutely nothing about nature. The physical content of Lorentz invariance is that nature has a symmetry under which scalar fields do not transform. Take, for example, the temperature of a fluid, which can vary from point to point. If we change the reference frames, the labels for the points change, but the temperature at each point stays the same. Like I said earlier, it's a scalar. A scalar, not a scalar field, is just a number. For example, h bar and 7 and the electric charges E are scalars. Under Lorentz transformations, 4 vectors transform as the thing as capital V mu over capital lambda mu upper indice, lower indice mu, and V upper indice mu. Like I said, it's usually a nice convention. If you're going to sum over indices, put one on the bottom or put one on the top. That's actually the only way you can do it. But because another thing the metric can do is that it can raise lower indices to bottom indices, and technically those indices have to do with whether you're dealing with vectors or covectors. Because, lol. Covectors, they're not important. Just know they exist, and most of the time it's bad notation if you write like summing over things like that. Anyway, switch. The transformation law, this defining property of a fourth vector. If mu nu upper is not just a number but depends on x, we write view of mu of like parentheses x and call it a vector field. Under Lorentz transformations, vector fields transforms just like four vectors. For a vector field, as for a scalar field, the coordinates of x transform, but the space-time point to which they refer is invariant. The difference from a scalar field is that the components of a vector field at the point x transform into each other as well. If you need a concrete example, think about how the components of the electric field rotate into each other under 3D rotations, while a scalar potential, for which E, uh, well, hope you know what a Laplacian is. Not a Laplacian, just like a gradient is.
No.
Oh God. Okay. I realized I've gotten this far, and there's not been a single point where the math has not just been easily explainable. That's gonna start changing really fucking fast. All right. All right. So, electric field. Remember, definable field is that at each point of space, you can think of it as just three slots essentially. A thing you can just slot these into. E field has X, Y, Z component, which you can point to. The E field is related by a Lorentz force law, which basically tells you that if you have a plus or negative charge, it'll just tell you how the particle will move along it if you solve for the equations of motion. All you know about is that because of the fact that the E field can be defined as having a zero curl if we're not doing it, not as statics, i.e. don't have to talk about magnetism, then you can define it as being the gradient of some scalar field, which is very useful because scalar fields are a lot nicer to solve for than vector fields. And this is just basically telling you is because the E field is defined by a scalar field, it is rotationally invariant. Well, all right, a vector field is a set of four functions of spacetime. A Lorentz invariant theory constructed vector fields has a symmetry. The result of calculations will be the same if the four functions are mixed up according to 2.18. For example, g mu nu, upper mu nu, times partial lower mu. You know what a partial is?
No.
Okay. Partials, they're really fucking scary. All you need, I don't know, I'm scaring you. They're derivatives, but they're general, meaning in the sense that if you have multiple coordinates, so like if you have a function depending on x, y, and z, it's like commonplace to write partial x and partial y instead of ddx, ddy. So it's like
Okay.
if your function depends on numerous variables, you just write partial. That's the
Okay.
layout.
Interesting.
It's literally just like a notation thing. Like no one writes ddx. It's 99% just partial. So if you ever see that, it's like, oh, this function depends on multiple variables. Anyway,
Okay.
cool. So partial mu means you're taking partial derivatives with respect to time, x, y, and z. It's a geometry thing, lol. And then you have partial mu times v mu, which means that you're not summing over them. I fucking god. All right. Vector calc. How do I explain this? Okay, so there's two different things you can do with tensors, because when I say multiplying, I mean the numbers are just right next to each other, but because the indices are different means you're forming a 2x2 matrix of those, because it includes all possible permutations of it. Because remember, the bottom indices go from 0, 1, 2, 3, and 4, meaning that if you want to construct it, that means you'll be doing 0, 1, 2, 3, 4 of all possible permutations. And here you'll get a 4x4 matrix, but that's because we're dealing with 4D. It can literally be whatever you want. But if they're the same indices, those indices have to be the same number. Meaning, like, if it was partial mu v mu, that means it would just be partial 0 v 0, which means you're taking the temporal derivative of its temporal component, partial 1 v1, which means you're taking the x derivative of a spatial temporal, blah, 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 and you add all those numbers together, and you get a scalar. Because the whole thing about tensors is, like, it basically tells you, okay, how do I collapse this into, like, a real valued number? Or more specifically, how many dual vectors and vectors are the ones that go on the bottom, upper indices, and dual vectors on the bottom. Don't worry about it. How many things do I have to shove into this object to output me a real number, essentially? The amount of indices on the object is also called its rank. So the metric being a rank 2 is a rank 2. Yeah, tensors are basically just dimensionally generalized mathematical objects which uphold nice symmetry. Or more general understanding for those mathematically inclined, it's a multilinear map of vectors and dual vectors to real numbers. Anyway, cool. As Lorentz invariant at each point, if and only if v mu transforms as a vector field under Lorentz transformations. If view mu x were just a collection of 4 scalar fields, g upper mu nu times partial mu v mu would be frame dependent. Some important 4 vectors are position. Remember t, x, y, and z. Derivatives with respect to x mu. So remember I said you can just think of it as just like the derivatives of the coordinates. So partial t, partial x. When we say partial t, that's just like partial with respect to. So partial t, partial x, partial y, partial z, and each of those correspond to their eluded vector component. So partial t would go in the temporal component, partial x would go in the x component, blah, blah, blah. Momentum, p mu, it's a e for the temporal component, smile, and then p, x, y, and z for its corresponding spatial components. Yeah, tensors transform with just a tensors transform. Tensor fields are functions of space-time, such as the energy momentum tensor or the metric tensor in general relativity. If we add more indices, such as get ready for this, all these are upper indices, mu, nu, alpha, beta, we still call it a tensor. The number of indices is the rank of a tensor. So I already said this already. When the same index appear, I already said this already. Cringe. Oh yeah. In general relativity, it's important to be careful about distinguishing vectors with lower indices, covariant vectors, and vectors with upper indices, contravariant vectors. When an index appears twice in a contraction, the technically correct approach is for one index to be upper and one index to be lower. However, that can make the notation very cumbersome. He is stupid. I don't know why he does this. If the indices are ordered, you must write view of mu upper equal blah, 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 blah. All you need to know is he does cringe notation. Anyway, continuing on forward. The simple Lorentz invariant operator that we can write down involving derivatives is the D'Alembert. Looks like a square because it's a stupid joke because the Laplacian is a triangle. So if you add another dimension or another line, you get a square. Lol. Anyway, the D'Alembert is defined as partial squared t, partial with respect to time squared, minus partial with respect to x squared, minus partial with respect to y squared. It's a 4-vector version of Laplacian, which is just here we go again. Partial with respect to x squared plus partial with respect to y squared plus partial with respect to z squared. And before you start getting me, yes, we are squaring these, but we're dealing with flat. We're dealing with not curvature, so don't worry about it. These are funny vectors.
Okay.
I didn't hear anything. Yeah. Finally, it is worth keeping the terminology straight. We say that such objects, v squared equals v mu on the bottom times v mu on the top. So like that's how you can times numbers together. Because phi, which is that, huh?
I'm breaking shit.
I'm breaking shit. 1 and partial mu times v mu on the top, which means you're doing that like plus 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 thing. That means if you do that, you'll get a number, real number. Are Lorentz invariant, meaning they do not depend on our Lorentz frame at all. While objects such as v mu, f mu nu, that's the Faraday tensor. We'll talk about that later. Partial nu and x nu are Lorentz covariant, meaning they do change in different frames, but precisely the Lorentz term dictates something such as energy density is neither Lorentz invariant nor Lorentz covariant. It is instead the 0,0 component of a Lorentz tensor, T mu nu. I.e. meaning that like the only thing that really does transform Lorentz invariantly is just purely scalars. Because the thing that we're all Lorentz invariants, we're just all scalars. Although they involve tensors in them, they're still just outputted scalars. Scalars are cool. Discrete transformations. Lorentz transformations are defined to be those that preserve the Minkowski metric. That's the most simplest case of just 1, 1, 1, 1, 1, 1. That's literally just Pythagorean theorem. It's just your flat space. Flat space meaning like your Pythagorean theorem makes sense because you have a space where your metric has like variables in it, means your Pythagorean theorem is just kind of curving in a sense. Like it's no longer like 2 straight lines; they could just start curving. So then you can get really funky technical triangles. Like I remember on the sphere, you can make like a triangle with more than 180 degrees in it, and still be a triangle. Yeah, that's a classic example. They also, equivocally, blah blah blah. Oh, parity. Oh, let's go over some basic transformations. There's something known as parity. So So you have a position of t, x, y, and z. Parity is you go t minus x minus y minus z. You just flip it. People say in the mirror, I think that's stupid. You just flip the coordinates. Time reversal is just you reverse the time on it. You can write these as matrices, and these are generators of certain groups. Parity and time are very important. Specifically, there's another one called charge. So this basically is like one of the main areas of particle physics, this thing called charge parity time. And there's a lot of different areas where they're violated. I know they're violated. By violated, I mean it doesn't uphold that symmetry. So that meaning that physics is different if you do parity, and physics is different if you do time reversal. That's true for the weak force, and that's true for the strong force. Strong force doesn't matter that much, but weak force it does, and which is an active area I'm researching. So we say that we already went over what that is. Oh, what I mentioned earlier about the light codes about being time-like, space-like, that actually has to do with the fact whether or not your space-time interval is positive or negative, but you don't need to worry about that. All right, cool. We're going to do a simple harmonic oscillator now. So, how long is it going?
What? How long we've been doing? Half an hour.
Well, we're just setting up the framework, which will be useful later. This is just
Oh
like,
my god.
oh, there's chapters of this. Oh god. Yeah, no. Yeah, no. The upper physics is like 8 chapters of math, and then you get to one physical example halfway through it. All right.
Fucking nuts.
Well, we're doing the harmonic oscillator, so oh god, there's a lot of math in here. Oh god, there's a lot of fucking math in here. All right, prepare yourself. Anything with a linear starting force, any conservative force is linear, close enough to equilibrium. You know what a force is, such as a spring or spring with tension, or a wave is a harmonic oscillator. For example, a spring has m times acceleration plus kx equals 0. Well, which is satisfied, or the solution to that being if you use differential equations, which is just cosine, which is just a wave. So it oscillates with square root k over m. A more general solution could be, c1 e to the I theta t plus c2 c subscript 2 e to the minus I theta t. So remember Euler's formula, which is e to the I t equals cosine t plus I sine t. Exponentials are nicer to look at than cosines. The classical Hamiltonian for this system is the sum of kinetic and potential energy, which is defined as 1 over 2 p squared over m plus 1 over 2 m omega squared over x squared. That the Hamiltonian being is the way you can define your quantum system. It's like very much like Newtonian mechanics, where you literally just have to define like things and then you get to solve for stuff. The Hamiltonian is like that. Essentially, most of the time, all you're really doing is just like inserting a specific potential in there, being like, what does this potential do? And sometimes you do stuff with like the kinetic energy, because the Hamiltonian is kinetic and potential energy. So 1 over 1/2 of p squared over m is just kinetic energy, and you write that momentum because momentum is nicer to work with than fucking mv squared. So, and well, more specifically, because there's a thing called the momentum operator, which is quantum mechanics. Lol, you know what that is. And then you have 1 over 2 m omega squared x squared, which is just the spring potential, because x is also a position operator. What's an operator? To quantize harmonic oscillator, we promote x and p to operators as opposed to canonical commutation relations. Canonical commutations are saying if I act this operator on a thing, how much does it fuck up if I reverse the order of it? So if I have a state, and if I like, oh guys, define what operators do. Operators do a lot. Operators don't really do much themselves specifically. There's certain things you can do with them. Meaning if you arrange them a certain way, you can get expectation values, which are actual real life numbers. Because quantum mechanics is like, if you don't see the word expectation value, it technically isn't real in a sense. Like no one has actually found the scalar, like complex scalar field of quantum mechanics, because that's not possible. You can only see things called observables, and observables are represented by these operators, which acts on states, and you get these states solved by the Hamiltonian, which is the thing I called for earlier. Basically, you get a Hamiltonian, you can realize states out of that, which then you act on those states to get variables you want. But you can only do it that way, because everything that isn't in like operator land is just not physical at all. because you have eyes in there. You have imaginary numbers in there, most of the time at least. So, and what commutations basically tell you is like how much do these things fail together, and it also encapsulates the mathematics of quantum uncertainty of your measurements. I like Heisenberg. Say my name. See, Walter White meme, whatever. Anyway, so all a literally commutator is a very simple thing. It's brackets with two variables in it. Let's call them A and B. It's be so much easier by adding a drawing and not doing it verbally. A and B. So, yeah. So commutator, the relation is defined by AB minus BA. That's all it is. For basically any math that is pre-quantum, that's always equals 0. Because 5 times 12 minus 12 times 5 is the fucking 0. Because things commute. But in quantum mechanics, operators don't necessarily commute. So in here, if you do that, like, so we have bracket x comma p bracket, which means just position operator of xp minus px acting on a state. Well, it technically is I over h, but that's because h is set to 1. But if there's supposed to be an h bar there, but it just equals I. Meaning that's where quantum uncertainty comes from, which means that you can only know so much of the position before your momentum starts to get uncertainty as well. Think of it as like a balancing act. Like the more you know of your position, the less you know of your momentum. So the classic example is like if you know perfectly, let's just say your momentum of it at one point, that means the particle could literally just be anywhere, like in space. Definably, it will literally just mean that there's an equal chance of finding a particle anywhere in space. Because the way you take observables is you integrate all over space, and it'd be like, where could it be here? Literally what you have to do for this. It's insane. So this meaning that there's always going to be a degradation upon which one you act upon first. And that also works in the math and whatever. Analysis of the harmonic oscillator spectrum is simplest if we change variables to, I'm not repeating that. Basically, if you take a Hamiltonian system from earlier and promotes these things called creation and destruction operators, which basically create blah, blah, blah. You do neat algebra with the fact that these operators behold certain properties, and you can easily rewrite the harmonic oscillator for a quantum system as just being omega, which is just its angular frequency. Parenthesis is a number operator, which just basically tells you which state of the energy you're at within a quantum oscillator. Because remember, this is quantum. Quantum doesn't mean you give him $50 million hedge fund funds. All quantum means is you're quantizing variables. Most of the time, it's just energy because you can't quantize many other things, but yeah, so energies are quantized, which means they can only exist at specific energy levels that which we can very much know to a degree. So for the harmonic oscillator, it's literally just like the angular frequency times what level that thing is at. Literally defined as like, I'm at level 2. I output the number 2. I'm at level 3. I'm at level 3. It just spits you out the number and plus 1/2. So it's like if I'm a level 2 quantum harmonic oscillator, I'm like h bar omega like 3 over 2.
Okay.
Really simple stuff here. You can get that result because of algebra manipulation that I think would probably take 3 years off my life if I tried doing verbally. It's really neat. It takes like a page and a half. Blah blah blah. These are also eigenstates, which means they're logical. We like them. They're coherent. Blah 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 blah. Okay, cool. Connection to special relativity. We connect special relativity to the simple harmonic oscillator. We note that the simplest possible Lorentz invariant equation of motion that fields can satisfy is the Ambritian of the phi equals 0. Remember, Ambritian is just the minus partial t respective partial with respect to time squared plus the temporal ones, but they're plus and they're different respective whatever. Laplacian with 4D in it. I'm giving up. The classical solutions are plane waves. For example, one solution is, oh, this is fun. Phi of x equals a of p, which is amplitude of time, because time, e to the I p vector dot x vector. Yeah, where partial t over partial t, yeah, anyway, you just do a bunch of math, and then you realize that, oh, you can realize particles within quantum harmonic oscillators, and you promote them. What else do I want to go over? You can define your Faraday tensor at B and P fields, but you don't even know what the hell that is. Oh, maybe I should have skipped the first chapter. Maybe this was a rookie mistake.
Oh god. I don't think it would make it any more clear though.
No, we're not. I can't wait to look back on this later and be like, "Oh, I explained it so badly." I think I've explained it well so far. If I had a blackboard and you had any knowledge of physics, if you had the prerequisite knowledge of physics,
Yeah.
more say.
Yeah, that would probably help.